Okay, guys. All right, so the next unit is average atomic mass. We're going to be talking about what the numbers in the periodic table mean. We already learned what the top one means. The atomic number means the number of what? Protons. Number of protons. Good. So today we're going to talk about molar mass. Now, molar mass is a really interesting thing. It is a ratio between things we can measure, grams, and things we cannot, atoms. So people have done lots of research. They're constantly doing research to figure out what is the ratio between the number of atoms of iron, which we cannot weigh, and grams of iron, which we can weigh. And the answer is the molar mass. Okay? So today we're going to talk about calculating average atomic mass, and then we're going to be doing molar mass on Friday, and moles and grams and atoms. We're going to basically be doing this all of next week. And we have some really slick labs next week too. Any questions before we jump right in? All right. First, the idea of the mole. You've probably heard about the mole in previous science classes. The mole is a crazy number that was found through experimentation, and it's kind of like a dozen. If you had no idea what a dozen was, and you walked into a donut shop and they're like, 1 dozen donuts. Okay, I'll take 1 dozen donuts. And they gave you how many? 12. You're like, oh, I got 12. I was expecting 1, but I got 12. Okay, great. And you walk out. Then you go to a florist and it says 1 dozen roses. You're like, okay, I'll take a dozen roses. And you get how many? 12. And you're like, I got 12 again. I was expecting 1 and I got 12. So that means a dozen must be 12. Get the idea? Well, that's what was happening hundreds of years ago. People were doing all these investigations with chemicals, and they kept coming up with this crazy number. And the crazy number they came up with was 6 times 10 to the 23rd. So we're going to call that Avogadro's number after a guy named Amedeo Avogadro. He did a bunch of crazy research, and for his research we honored him with a very important name, the mole we're going to call Avogadro's number. It's 6 times 10 to the 23rd. Now you're going to run into people who are going to be like, it's technically 6.022 times 10 to the 23rd, which is true, and it keeps going on. But for our purposes of what we're going to be doing, 6 times 10 to the 23rd works pretty well. Okay? The 0.022 I'm not really going to care about. You want to use it? Go for it. I'm just going to go 6 times 10 to the 23rd. You're not going to even have to use something called significant digits until chemistry AP or physics AP, so don't even worry about that. Okay? But it's a very important unit. What it basically means is, if you dig up 6 times 10 to the 23rd atoms of iron, you will have 1 mole of iron, and that 1 mole of iron will weigh 55.8 grams. So this mass down here, from now on, we're always going to read this as gram per mole, like 12 donuts per dozen, and 12 flowers per dozen. We're going to read that number as grams per mole. Okay, questions? Then off we go. So quick review. When you're looking at the periodic table, you're always going to see the same thing. You're going to see the name, which may or may not be English-like, depending on if we're still using the Latin name. Okay. We learned last unit that the number of protons is the atomic number. So all oxygens have 8 protons. All tungstens have 74 protons, because the atomic number for oxygen is 8, and the atomic number for tungsten is 74. Okay? It's really, really handy. If you add a proton, it's no longer oxygen. It becomes fluorine. Okay. The atomic symbol, of course, we slap it in the middle. Sometimes it's like the name, sometimes it isn't. Okay? Some things are very easy, like nitrogen and oxygen. And we learned earlier that there are things that have a Latin root, like lead is Pb because the Latin name for lead is plumum. And iron is Fe because the Latin name for iron is ferrous. Actually, kind of cool. I think ferrous is a lot cooler than iron, but whatever. Now, the interesting thing is this. They show the molar mass, or they show the they show the molar mass on the periodic table, not the atomic mass. Because the atomic mass is the sum of the protons and the neutrons. And to dispel the bad learning that you were taught years ago, no, the number is not half protons, half neutrons. Some people are still, but I learned in 6th grade that the number of protons and the number of neutrons are the same. But they're not. Okay? Sometimes they are, but they're not necessarily the same. So again, the atomic mass is not half protons, half neutrons. It is just the sum of the protons and the neutrons. So, some of you are madly scribbling, so I'll give you 10 seconds to scribble and maybe think of the question that I'm about to ask you. We remember that chlorine's atomic mass is 36, and its atomic charge, or nuclear charge, is 17. So that means 17 minus, which is the number of protons, minus from the mass, gives you your 19 neutrons. Okay, so my question for you is this. Why don't we show atomic mass? Why do we show molar mass down there?
Because molar mass stays the same for each element, but the atomic mass changes depending on how many protons and neutrons there are.
Okay, you're kind of floating around the general idea. Yeah. Sophia? That's true. It is more difficult to calculate, and you've both got a piece of it. Anyone else want to come up with an idea? You're going to have to calculate something, and it's not just the protons and neutrons. Okay. Yeah.
Does the molar mass include like electrons?
Kind of right. Yeah, that's also true. It also includes the mass of the electrons. But the reason we don't show atomic mass, we show molar mass, is because every element has isotopes. And what we want to show is the average of all those isotopes. So molar mass is the average of all the isotopes we're going to dig up. When we go dig up some iron, we're not just going to find iron 55. We're also going to find some iron 56, iron 57, maybe some iron 54. We're going to find several isotopes of that iron because we cannot just dig up iron 55. When we dig up iron, we're going to get all the isotopes. So what we use is the average. That is an average that is useful to us. And it's a weighted average of all the isotopes of that element. Yes?
I'm still confused because, I mean, when you're adding, okay, so atomic mass is your protons plus your neutrons.
Mm-hmm.
But, like, when you add 8 plus the 8 protons plus 8 neutrons, you still get that number.
Okay, if I gave you a balloon of oxygen, in that balloon of oxygen, there are billions upon billions of oxygen atoms. Some of them are oxygen 15. Most of them are oxygen 16, but not all, and some are oxygen 17 and 18. So you cannot discriminate out the oxygen 16s, so we have to use an average to say the mass of the oxygen I have is an average of all the oxygen atoms. And it comes from a natural abundance. It's kind of like this. If somebody said, "What's the height of your students in your classroom?" I'd be like, well, it's going to take a long time to write them all out, so let's take an average. So we take everybody's height, we add them all up. Some people are like 4'6", and some people are like 6'9", and we add them all up, and we find their average, and then we say, oh, the average is 5'9". Okay, that makes sense. That's the number we could use. Okay, does that make sense? Similarly, if somebody said, what's the weight of oxygen? And I said, well, we got a whole bunch we got this 50 billion that are oxygen 16, this 2 billion that are oxygen 18, this billion that are oxygen 6, and so on. So instead of doing that, we just give them an average. And it's a weighted average. The weighted average takes into account the more of one than you have of another. Where have you used a weighted average before? Yeah, GPA and your grades. Your GPA and your grades are weighted averages. Okay? So if you take a 2-credit course and you get a C, you get more oomph if you take a 4-credit course and get an A. Make sense? That'll make sense when you go to college. Okay, but when you're doing your semester grades, that's a weighted average. It's not a simple average, it's a weighted average. So you're in December, you're all going to come to me and say, what do I have to get an A in the class? And I'll be like, well, do the math. You know that your semester exam is 20%. You know that quarter 1 is 40%, and you know that quarter 2 is 40%. This is a weighted average. Quarter 1 and quarter 2 are weighted heavier than your semester exam. So their score counts more. Similarly, oxygen 16, there's a lot more oxygen 16, so its average counts more. So let's do this weighted average. Okay, what are you going to get on your semester exam?
86.
An 86. Okay, so you got an 86 on your semester exam, and we're going to multiply that by 20%. Guys, percent means per how many decimal points?
0.2.
2. So 20% becomes 0.20. And what did you get for quarter 1? 93%. Okay, 93%, and it was weighted at 40%, so that's times 0.4. And what did you get for quarter 2?
82.
82%. Slacked off a little bit. You were like Thanksgiving, all tired. So 0.40, and then you find the chunks, and then you just add them up. So go ahead and do that. See what your score was using a weighted average. Now, the thing about any average, weighted or simple, the average will always fall higher than the lower number and lower than the higher number. That's always going to fall inside that range. So you should get a number between 82 and 93. 87.8. So when you added this chunk to this chunk to this chunk, you got 87.8. 87.2. 87.2. Okay. Does that make sense? So you add this chunk to this chunk to this chunk, and you get your calculated grade. The computer does it for us. So you're like, what do I need to get? You can just do the thing, and then you can work backwards if you want. And I'm. All right, cool. Okay, now I do want to talk about a pitfall. The pitfall about percentages, some people get really confused on certain types of percentages. Now, some are very, very easy. So for instance, if I gave you 35%, you're going to put that in your calculator as what? 0.35. But if I gave you 1%, you're going to put that in your calculator as what? 0.01. Good. You're seeing it like, oh yes, my math teacher warned me about this too, 0.01. And if you got 0.1%, you're going to put that in as what? 0.001. Good. Okay, I'm going to leave these up here for today's practice. So be careful with percentages. Some people somehow in their brain, they're like, well, if it's already one digit, I don't have to move the decimal. You always have to move the decimal. Okay. How are we doing about this? Okay, so let's move back to chemistry and talk about average atomic mass. Now it works with what's called a natural abundance. The natural abundance is the natural percentages of various isotopes. So the natural abundance of oxygen 16 might be 85%. The natural abundance of oxygen 17 might be 2%. The natural abundance of oxygen 15 might be 4%, and so on. And here's the goofy thing about natural abundance. It's constantly changing. As our world and our universe ages, the natural abundance of all the elements on the planet are constantly changing. So every few years, your periodic table has to be updated. So if you're like, Mr. Byers, my periodic table is different than what I found online. the one online actually might be updated. It might have been updated last week. Because the natural abundances of all the elements are constantly changing. My question for you is, why? But we don't. When I eat a hamburger, the atoms in the hamburger end up in my poop. They don't actually change.
The half-life stuff.
Exactly. What about the half-life stuff? So what's going on?
Well, elements are constantly decaying.
Yeah, exactly. Elements are constantly decaying into things. A carbon-14 is turning into a nitrogen-14. A uranium-92 is turning into a thorium-90, and so on. Or sorry, a uranium-235 is becoming a thorium-230 or whatever. So yes, because nuclear reactions are happening and atoms are constantly decaying, the periodic table is constantly in flux. And it will be constantly in flux forever. So if you want to make sure you always have a job, become a chemist and just experimentally find the masses of the elements constantly. Yeah?
What would hydrogen decay?
Hydrogen wouldn't. Yeah, hydrogen's the simplest. So there are hydrogen 2 and hydrogen 3. So hydrogen normally has one proton, but there are hydrogens called heavy hydrogen that has a neutron, making it hydrogen 2. And there's really rare hydrogen that has 2 neutrons, making it hydrogen 3. So the hydrogen is constantly decaying. Those 2 and 3 hydrogens are decaying into other things. So hydrogen 1 will never decay into anything. It's the simplest thing. But there are hydrogen 2 and hydrogen 3 that are decaying down to hydrogen 1.
I was just wondering if the cadence of electrons are.
Not that we're aware of. Not that we can detect. 1 then 2.
Wait, so you said natural abundance is the percentage of what?
The percentage of all the isotopes that exist on our planet.
So, back to the hydrogen thing.
Mhm.
So, when everything decays, it just kind of becomes hydrogen, it stays as hydrogen?
Not really. There are things that decay and stay stable. So not everything will decay into its simplest form. There are elements that they'll decay, boom, and they're stable, and they'll be that way for the rest of the universe. Okay, so let's calculate them. So again, isotopes have a mix of elements have a mix of several isotopes. Same element, remember, same elements, the same number of protons, isotopes different in neutrons, and you probably already figured it out, but if you like to see things on the screen, you take the isotope mass, multiply it by relative abundance, isotope mass multiplied by relative abundance, isotope mass multiplied by relative abundance, and then you add those chunks up, just like you did with the grades. You just take abundance times mass, or mass times abundance, mass times abundance, mass times abundance, and add all the pieces up together, and you'll have the average atomic mass of that element. And for the rest of the day, we're just going to practice it. Yeah. This is all we're learning today is how to calculate average atomic mass. And some of you are like, I already figured out how to do it because I did the weighted example with the class. And so I did work at the class. I already know how to do it. So take another minute to scribble what you want to scribble, and then we'll do our practice exercises. And again, I'm sorry some of the reds don't show up in the screen. Projector's not excellent. But if you want to move up, you're always welcome to move up. Oh, we have really got to talk about your notes discipline. Don't just write everything down you see. Don't just mindlessly like a robot write everything down you see. Sum things up, write them in your own words. Use shorthand. If something is super obvious, don't write it down. If you're like, I already know what an isotope is, then don't write that whole first paragraph down. Okay, so practice, here we go. Average atomic mass practice. Consider the mythical element Wagnerium. Wagnerium has 3 isotopes. Wagnerium 18 is 25% abundant. Wagnerium 19 is 60% abundant. And Wagnerium 20 is 15% abundant. Using the rules that you have, calculate the average atomic mass of naturally occurring Wagnerium. Would you like the lights on so you can see your calculator? No? No? Okay. Some people are like, I have a solar. I have to have lights. And again, as a little bit of a check, the number you get should fall between the highest and lowest value. So you should have a number that falls between 18 and 20. The other pitfall about calculating average atomic mass is you don't turn it into a simple average at the end. You don't take your answer and divide by 3. The weights do the dividing for you. So you just do part times abundance, part times abundance, part times abundance, add up the chunks, and you're done. You don't have to divide by 3 at the end, because it's not a simple average. It's a weighted average, and the weights do the dividing for you. So in a weighted average, it is the weights that does the dividing for you. You don't have to divide it again. A simple average, and you add them all up and divide by how many you have, it's not a simple average, it's a weighted average. So after you add up the 3 pieces, you're done. Who needs more time? Okay, 1/2 more minute. 1/2 more. Well, 20 seconds now. All right. If you got a number larger than 18, raise your hand. All right. If you got a number larger than 19, raise your hand. Oh, good. So you added all the pieces together and you got 18.9 gram per mole?
Yes.
Yay. Okay. One more before I hand out the worksheet. Consider the element gallium. Gallium has 4 isotopes. 34 AMU is 12% abundant. 35 AMU is 25% abundant, and 36 AMU is 36% abundant, and the 4th isotope, 37 AMU, is 30% abundant. So on your own, please calculate the average atomic mass of naturally occurring gallium.